Any general questions before we get started? Any genetic algorithm questions before we get started? Any questions? Yep. Sorry, what was that? I might take a look at it after introduction if you want to chat. Well, let's get started. So lab activity 9, I don't have the doc up, but just especially for the people who have lab tomorrow, I want to give you a heads up on what's going on with that. Lab 9, it'll be similar to lab activities 1 and 8, but for the last homework. So my goal is to get the homework doc out by tomorrow morning as well. So get the initial code for the last homework and just make something happen. I might get a little more specific on what that something is this time, but in general, just something has to happen. The last homework is going to be all about pathfinding. So you'll be given a GUI where you'll have a map as a grid laid out in the GUI, and then it'll listen for mouse clicks, and your goal is to move an object from wherever it is on the GUI to wherever the mouse click is. Now, to start, just moving the object over to that spot, not too tough, but then we're going to throw in the impassable tiles, and eventually, potentially having this as a complete maze that you have to navigate the entire maze. So by the end of the homework, you should be able to write a maze solver to be able to find any way through any grid map with impassable tiles. So for the lab, just taking the initial GUI, the click won't do anything on that GUI, you'll just have probably just a circle on a grid. And then your goal is to respond to those clicks in some way, just move that thing. Maybe move it, just teleport it to the click will probably be the objective for the lab. And the homework will be just increasingly complex, how to move this object to where we clicked. Lecture question today is a bit more involved. This will be true for the last 4 lecture questions, the next 4 lecture questions, I should say. My goal is to get 400 points of lecture question out there, so I was running the numbers and look at what we had. We have 300 points out there already, 320 with this question, so I'll have 4 more lecture questions, each worth 20 points, just to make sure we can get up to that 400 total points available to make it so you can miss 100 points and still reach your 300. So 20 points. Due tomorrow night. I've been doing this for the last 3 or 4 lecture questions, but I never announced it. But the lecture questions, I'm having them do the following midnight instead of the midnight of lecture for these last ones. And these last ones, they'll all be 20 points, and they'll be fairly more involved. So for this one, we'll talk about what expression trees are, of course. We don't know what they are yet, unless you read ahead. But evaluate an expression tree and resolve it to a single value. So, what's a tree? What's an expression tree? Let's talk about it. So, binary trees is what we're going to talk about today. There can be general trees in computer science, but binary trees is what we'll focus on for this. What we mean by this is we have a structure that's very similar to a linked list, except we can have 2 next nodes. That's really the only difference between linked lists and trees. But there are a lot of implications to that make trees more useful in many situations because we have this kind of branching structure and also a little different to work with. So each node can have 2 nodes that it refers to, and just a little bit of vocab and nomenclature. When we talk about trees, it's common to use the family tree analogy. So we say that those 2 nodes are the children of that node, and that node is the parent of those nodes. Then you can extend this, you can have grandparents and cousins and all that. We won't really need all that vocab for what we're going to do in this class, but just a heads up that is the vocab associated with these trees. You'll see these again in CC 250, and you'll use all that vocab. So child nodes, at least child nodes and parent node we'll use. The extensions, not so much. So this looks In memory, something like this. So say we have a variable named root, which is referring to the root node of this tree. We'll have this variable named root, which will store a reference to this node. And each node can have a left and a right child that it refers to. So this root node refers to 2 and 8. Each one of these nodes have 2 child nodes. And then we can go down and have child nodes until we have a node that's null. And that's the end of, I guess there is some more analogy here, is until it gets to a leaf node, which will just have 2 nulls. And this we would call a branch of the tree. There's a lot of terminology that's just borrowed from family trees and from physical trees. The one big difference is the root, we always draw it at the top instead of the bottom, and trees grow down. So this is the structure of a tree. This is what it would look like in memory. Each node has references to up to 2 other nodes, and any one of those nodes can be references to null, which is kind of the termination of that branch of the tree. All right, any questions on this so far? Because this is mostly what I'm going to say about the structure of a tree, and then we'll just talk about applications of this from here on out. Yes?
One null and then one.
Yes. So can a node have 1 null and 1 reference to another node? Yes. So I drew this as what we call a perfectly balanced tree, where every node, where every branch has the same number of nodes in it. But we could have, say, 2 referring to -3 and null null here, and refer directly to null here. So we don't have to have exactly 0 or 2 children. We could have just 1 child, and then the other reference equal to null. I just drew it because, I don't know, it looks pretty on a slide when I have it fully balanced like that. In the code, this is the entire code to be able to build that tree on the previous slide. I'm going to create a binary tree node class, similar to the linked list node before we had any methods inside of it, that just stores the value at that node, a reference to its left child, and a reference to its right child. And there's no simple way to, say, add and remove elements from a tree. There are ways to do it, again, you'll see in CC 250. But for now, we're just going to manually create our trees. So I'm going to create my root node and just manually say root.left equals this new node, root.right equals this new node, the root.left is going to equal this node, and just manually build the whole tree structure out from there. So I'm not getting too fancy with this. You will next semester, if you take 250 next semester, be building these trees and just having an add method. How do I insert an element into this tree? We're not going there in 116. I just want to expose you to the structure of a tree and kind of get you used to what's coming up ahead with trees. So with that, manually building the tree based on this class, and that's how we can have that whole tree from the previous slide, a root of 5, it's left 2, right 8, etc. All of it's right here in this code, and we have that exact tree that we visualized last slide.
When doing vowel root using binary 5 to 8 circumvent the next two ones.
Does it circumvent the what? Sorry, what was it?
Root dot left and root dot right lens.
So when I create this root node, left and right are both null, and then I'm overwriting, I'm saying left, hey, instead of being null, you're going to be this node. And then right, instead of being null, you're going to be this node. And then I overwrite these 4 nulls as well. But then all these nulls remain. I just leave those as null. So I'm creating a node of 5 that points to null and null. And then I'm saying your left is going to equal this new node, your right is going to equal this new node, and your left is going to equal this new node, your right is going to equal this new node. So I'm replacing those nulls as I'm building the tree, but leaving the last 8 nulls is all null. So we know where these branches end. Any other questions? you have questions, please ask them now, because we're going to move on. This is all I really have to say about the structure of a tree. The rest is algorithms. How do we work with this data in this tree structure? So I want to make sure we understand the structure first. It's right here in the first line?
Yes, put 2 and 8 here. So you can put it to a line.
Yeah, so this node is going to be right here, and this node is going to go right here. Is that what you're asking about?
Yeah, you can write it like that. Like right.
Oh, could I write it the other way around?
Yes, like
Yep.
2 and 8 and those.
So I could say, like left node, val left node equals this, val right node equals this, and then val root equals new binary tree node 5 left node right node. I could write it like that as well, yes.
So you have to initialize that and write separately first.
If I did it that way, I would. I'd have to store those in variables because I want to create them, remember the reference, and then be able to give that reference to the root node when I create it. So it'd be, so I'd have to create a few more variables, but yeah, we could certainly do that.
You can't do that on the first line, 2 and 8 in there, it just can't work.
You, just this first line with,
2 and 8 in those 2 lines.
not with just 2 and 8 because these have to be binary tree nodes,
Okay.
but we could do binary tree node 5 and then have all this new binary tree node 2 null null and put that right here. And then this whole thing right here as well. We could do that. In fact, we could do all of this in one giant long line. We could have the whole tree structure built all in one line like that. But it wouldn't fit on a slide very nice if I had a one big long line. This is the big reason not to do that. Besides stylistic choices, usually don't want lines that are too long. All right, let's talk about how to work with this data then. So what do we do with these? With linked lists, whenever we had an algorithm on a linked list, I showed you a recursive way of doing it. I'm going to do whatever we need to do to a single node, and then recursively call that method, whatever we're doing, computing the size or calling for each, whatever we're doing. Recursively call that on the next node, and then have a special, have our base case of our recursion when we hit the end of the list. So when the next reference is null, then we're going to return and return back up the recursion. So that's how we did it with linked lists. But now with trees, we have 2 references. So how are we going to make sure that this recursive call works on both of the children, both of those reference nodes that we have, and have this recursion applied to both of them? So there's 3 different approaches to do this that we'll see: pre-order, in-order, and post-order traversal, to be able to do something, whatever it is we're doing, to the entire tree, whether we're just calling for each or just printing the values. A lot of my examples, I'm just printing the values to show the concept of the traversals. But whatever we're doing with these traversals, computing the size maybe, let's see how we do that with these 2 recursive calls and talk about the 3 different approaches here. So let's start with pre-order traversal. With this, we're going to do whatever we need to do, call a function in this case. I want to just visit every single node in a tree and call this function on every single node on that tree. For our examples, that function is just going to be printline. So if I do call pre-order traversal on the root node and say printline, I want to visit every single node in the tree and just print out its value. That's all I want to do for this example. So for that, we'll call the function on the value at whatever node we're visiting, and make 2 recursive calls to each of the children. Call this traversal function on both children of that node, unless this node itself is null. And if we got past the null reference, don't do anything. That's the base case of our recursion. Otherwise, call this function and then make the 2 recursive calls after that. So pretty simple, 5 lines of code, and we got there, where we have a traversal, a way of visiting every single node in the tree, and calling some function on every single node. So we call this a pre-order traversal because, as you'll see, as we'll talk about in the next bunch of slides here, we have 3 different traversals that we'll talk about. And the big question is, okay, we know we're going to make these 2 recursive calls, but when do we call this function? When do we actually do the thing that we're trying to do here? This is pre-order traversal because we're doing it before the recursive calls. Next, we'll see post-order, where we just put the function call after the 2 recursive calls. And then in order, where it's right in between. So we have 3 choices. We're just going to see what the difference is between each of those 3. Each of those 3 choices that we can make. So pre-order traversal, if we look at our tree and do a pre-order traversal, we're going to print these in this order. So we're going to visit the root first, print it, visit the left child through a recursive call, print that, visit the left child through a recursive call, print that. 2 nulls, that just returns and does nothing. Go to the right child, print that, check its 2 children, does nothing, return back up, call it on the right side, print that, left side, print that. 2 recursive calls that do nothing, return, the recursive call, print 14, 2 nulls, do nothing, and then return back up the recursion and exit end the recursive calls. So each time we visit a node, starting with the root, we're going to call the function on that value, make the left recursive call, and then make the right recursive call, and do everything for each one of those. So we're effectively going all the way down the left subtree, and then going back up and visiting each right node as we go back up. Post-order traversal is just the other way. We're going to make our 2 recursive calls and then visit the node's value. So the only thing we did was change this function call to after the recursive calls. Small change in our code, but makes a significant change in the functionality of the traversal. So here, instead of printing this right away, we're going to make our 2 recursive calls first. Recursive call on the left, recursive call on the left, recursive call on the left does nothing, recursive call on the right does nothing, and then finally print -3. Return, recursive call on the right, recursive calls that do nothing, turn out 4. Returns, 2 is done with both of its recursive calls, so now it's going to call the function on 2. Print that to the screen, go up to 5. It's done with its recursive call to the left, recursive call to the right, recursive call to the left, recursive calls that do nothing, print 7. Return, recursive call on the right, recursive calls that do nothing, print 14. 8's done with both of its recursive calls, so call the function. And the root is finally done with both its recursive calls, so print out the root, and then return back to whoever called the traversal. And finally, in-order traversal. So let's put the function call right in the middle here, and call this function in between both recursive calls. And for this one, I forgot I had a summary slide here. So in order, pre-order, post-order. This is where, with linked list, I forced the recursion a little bit. Most of those algorithms you could write iteratively with a loop, no big deal. These ones I want to challenge you. If you think, why would I ever want to use recursion? These ones I challenge you to write recursively with loops, or without any recursion, iteratively with loops. These ones are very simple to write using recursion, and this is true with most tree algorithms, including your lecture question. I challenge you to write actually I'd rather you write the lecture question recursively, but if you haven't done any recursion. But it'd be a nice challenge if you're really scared off from recursion. Just try to write these iteratively, and hopefully you'll see the power of recursion, of why that is useful sometimes. Why we even bother talking about recursion at all? Well, if you technically can do everything with a loop, just try rewriting these as loops. It's very possible. You can do it. It's just a lot more difficult than the linked list algorithms. It's something where you should start seeing why we use recursion. It can really simplify some operations like this. All right, But I went through those traversals very quickly. I did that on purpose just to expose you to those. But with the in-order traversal, let's slow down a bit and look at this step by step and see everything that's going on to see how this traversal really works and compare it to the code. So let's keep the code up here and step through this thing. We're going to call in-order traversal on the root node with the function print line. So again, we're just printing each element on a line of its own. And let's step through this. So the very first thing, we're going to call in-order traversal on the root node. And of course, I got enough packed in this slide. I can't show all the stack frames, but I'm going to visualize the stack frames as these boxes. So I'm going to create a stack frame of in-order traversal on the root node onto the stack. And I'm going to run through this. The node is not null, so I'm going to put another stack frame onto the stack, another function call of the left child of this node. So I haven't done anything. I haven't called the function at all. I'm just going to go to the left child and put this frame on the stack. This frame is still on the stack, but it's inactive right now. So I have 2 frames on the stack, at least 3, depending on where this was called from, a main method probably, at least for this. Doesn't matter. Anyway, I have 2 frames on the stack. 2. The node is not null, so I'm going to recursively call this on its left child. Now I have 3 calls on the stack. All 3 of these calls are at the line in-order traversal, waiting for that in-order traversal of the left node to resolve. So now we're at -3. We're going to recursively call this on its left child. Now the node is null, so that does nothing. It just returns. We're going to go back to -3. This call just returned, so we're on this line. We're going to print -3 to the screen. And then go to the next line, the next recursive call. That is null, so the method call does nothing. Returns. -3. Finish its 3 lines of code, so it returns back to 2. This node just got the return of its left node, so it's going to move on to the function call. Print 2 to the screen, go on to its right recursive call. Now when it goes to the right recursive call, we put a few more frames on the stack until we get here. That's null, does nothing. 4, print that. 4 just visited its left node, called its function, and now it's going to its next recursive call on the right. That's null. Nothing to do, return. 2 got to the end of its code, return. And 5 just got the return of the recursive call on the left, so it's time to print 5 to the screen, and then make its recursive call to the right. Recursive call to the right, 8 is going to recursively call it to the left, recursively call it to the left, null, return, do nothing. 7 calls its function, makes its recursive call to the right. There's nothing to do on the right, so it returns. 8, time to print out 8, make its recursive call to the right. 14, it's going to make its 2 recursive calls that do nothing, and in the middle, call its function, print 14 to the screen, and then return, back to whoever called this traversal. So the order in which we make these recursive calls is going to make all the difference in what kind of behavior we get. In this case, the order in which we visit the nodes. So here, since we have the function in the middle, we're visiting this node right in between traversing its left branch and its right branch. And once we're done with the left, call, and then go to the right. In order traversal, debatably, arguably, probably, is it even arguably the most useful traversal in order. And if you notice, the way I set up this tree, this is just a little prelude to Wednesday's lecture on binary search trees, is every left child is less than their parent, and every right child is greater than their parent. As long as I have this property and I run an in-order traversal, I'm printing out those numbers in sorted order. I'm visiting those numbers in sorted order if I have that property, and I do an in-order traversal. So something very useful for binary search trees that we get from that setup. All right, any questions on traversals? What's the advantage of this structure? There's information that we couldn't really, like it'd be difficult to, we haven't really gotten to that one yet. When we see the application, we're going to see expression trees, and it'd be very difficult to represent that information in, say, a linked list or an array or a key value store. There's certain types of data that just have this tree-like structure, so we want a data structure that's going to capture that information. If we're not concerned with data that requires this structure, in the case that we have on the screen now, if we want to store values in a sorted order, and some of this we'll get into on Wednesday, we want to store values in a sorted order, but also have fast operations on that sorted order. For example, if we have a sorted array and we want to add an element to it, and the element happens to be smaller than any element in the array already, we have to do an insert at the front and copy everything over one space, which is going to be an O of n operation. We have to copy over every value. If we have a linked list and we want to store it in sorted order, well, we have the same problem, but what if we want to add a value that's greater than everything in the list? We got to append to the end, which we know is slow. We got to navigate the whole list and append, or we have immutable lists and we got to copy the whole list. It can be tough. Even if we have a doubly linked list, which means each node has references to its previous and next, and you store the tail instead of just the head. Even then, what if you have to insert directly in the middle? You're not going to store that reference too. So a lot of slow operations if you want to store a sorted data structure. You want to store elements in sorted order, have fast inserts, fast removals, and fast finding. If you do this with a tree structure, you can get log n for all of those operations. So you can have a lot of efficiency and a sorted order. So that'd be one of the big applications of a tree structure. Yes.
Would you always have to build your tree class, or is there a built-in install?
They're built-in tree classes, yeah. In Scala, I forget what it's even called. But there are a lot of built-in data structures in each language that use trees without really advertising that they use trees. Trying to think of an example. I'm blanking on it right now, but there are some data structures that just use trees, but they don't really tell you that they use trees. Really, if you have a data structure built into a language that does maintain a sorted order, the odds are that it is using a tree. Because there's really no other way to maintain a sorted order and have efficient operations without using something like this. Another application, expression trees. If you're going after that bonus assignment, this not directly applicable to the bonus assignment, but it should help you understand what you're doing a little bit more with that one. And certainly related. And obviously related to the lecture question today, expression trees. How would removal of an element go for the children? Not always well. Removal, this is more of a 250 topic, but I'll very quickly talk about removal. If I want to remove an element by name, so say I want to remove 7, that's no big deal, I just remove it. But what if I want to remove 8? Now I have to fix this tree so it maintains the properties that I want, namely the left node of every node is less than, right node is always greater than, or equal to. If I want to remove this, I have to fix this tree. So I have to find a valid candidate and then move that node up to the node position that I just removed. So we would find this, put it up here, and then maintain that structure. In general, if I say I want to remove the root, I would go to its right subchild. Oh, geez, am I going to... If I can do this from memory, I might miss a small detail here. I'm going to try to do this from memory. But you go, if you want to remove the root, you go to the right subchild, and then keep navigating its left subchild recursively until you find a leaf node, a node with two nulls, or a null and a value in which you would do this recursively remove that node as well, and then swap. So if I want to remove this root of this tree, I would put 7 up there, and I know that I maintain all its properties. If 7 had a right subchild, I would call this recursively. I would remove 7, find its replacement, and then put 7 in the root's position. Or we could do it the other way around and go left, and then continually go to the right and swap that up. And that maintains all our properties. But again, that's a 250 topic. You'll talk about a lot of things. I'll motivate another one at the end of this lecture as well, about something that can go really bad. Sorry, at the end of next lecture. Something that can go really bad. With that 250 is going to address. But let's talk about expression trees. So, we have an expression. For the homework, we have an expression as a string, and you want to evaluate that expression. But there is another way to represent expressions, something that most of us probably won't really do, but it's something interesting, it's fun to show. If you're writing compilers or interpreters, you'll get into this kind of stuff. You'll tokenize like we do in the homework, and instead of just evaluating the expression right away, you would throw it in an expression tree to be able to get different functionality. I believe there's a lot of useful applications of these in that arena. Most of us won't go on to write compilers and interpreters, but if you do, if you're one of the lucky few, I don't know about lucky few, but if you're one of them people, this might be one of the things that you'll do. So, for an expression tree, we're going to represent each operator and operand as a node in the tree, and each time a node is an operator, it's going to compute its left subtree with that operator on its right subtree. So if I have this expression and I want to represent it as a tree in that structure, I'm going to write it like this. And then any leaf of the tree, so any node without any children, is going to be an operand, which is going to be just a number in this case. So each of my leaves are numbers, and if a node is an operator, it'll have 2 children, which are its operands. And the operands can be more operators. So this addition is 8 plus another operator, so 8 plus the division of 9 divided by 3. So that's how we get our order of operations in this. If we evaluate this tree structure based on each node, we're going to get the evaluation of this expression. So, if I want to evaluate this, of course you have to write the algorithm, most likely recursively, unless you want the extra challenge of doing it iteratively, or if you're that afraid of recursion. If you want to evaluate this subtree, you'll have to find an operator that can be evaluated. This subtraction can be evaluated because we have 2 numbers, and take 12 minus 4. Replace that, or in a recursive call, return the value 8, the evaluation of that expression, and find the next one that you can evaluate, 9 divided by 3, 8 plus 3, 8 minus 11, and it evaluates to negative 3. So you think about how to evaluate, how to write those recursions. Given this tree, I call evaluate on the root. It's going to involve 2 recursive calls to evaluate on its left and right, and then compute its operation on those 2 return values. But it's up to you to figure out, okay, what do I do in each case? If I have 2 nulls as leaves, or I have 2 operands, or if I have an operand and an operator, how do you handle all of those situations? Okay, let's revisit our traversals and run some traversals on this expression tree, because, I don't know, why not? I'm going to write a slightly modified version of the Inorder Traversal, and that if I have an operator, I want to add parentheses, and what I want to generate here is a fully parenthesized expression, which means any place where you can have parentheses, add them in. Even if they're redundant according to the order of operations, we're going to add parentheses every single place where we could add parentheses. So we want to generate this expression. So like we're explicitly putting the parentheses around here to say that this is evaluated first, even though order of operations should take care of that. But we just want to add a fully parenthesized expression. So to do that, if I'm looking at an operator, I'm going to add my parentheses, and then do an in-order traversal, and my function call is going to be just print with a space, which we'll see on the next slide. So if I just print whatever the value is at that node, followed by a space, if I do, I gave the whole thing away here. So if I do an in-order traversal with these parentheses, on that tree, I will end up with this expression. I'll have my fully parenthesized expression. If I call this fully parenthesized in-order traversal on the root node, I'll actually get my expression in a human readable, we have some redundant parentheses, but a human readable infix expression by calling the in-order traversal. If we call a post-order traversal, we'll get the postfix expression from this expression tree. So the expression stores all the information of an expression, and depending on which traversal we use to visit each node in this expression, we'll get different representations for it. So if we go to that tree that we had, that expression tree, which is representing the same expression from last lecture, and run a postfix expression completely unmodified, we're just going to run our standard post-order traversal because we don't need any parentheses here. In postfix notation, we will get our postfix expression out of that. Or reverse Polish notation. If you're Googling this, sometimes people like to call it reverse Polish notation. Just a heads up. So if we do our post-order traversal on here, we'll start at this node, visit the left, we can print 12, return, visit the right, print 4, return, we visited the left and right, so it's time to print this. Recursive calls, print 8, return, recursive call on the right, call on the left, print 9, return, print 3, return, print divide, print plus, print minus. So we get exactly our postfix notation expression. So just having the same tree and running two different traversals on it, we can get our infix or postfix notation for this expression represented by the tree. And this is one case where trees are just the right data structure to store this expression. If you try storing this expression in a list or an array, it's going to be kind of tough. Sure, you'll find a way that you'll be able to do it. But it's a little tougher to represent. This really has naturally this splitting structure where we split into the left and right-hand side of the operator. It very naturally fits into a tree when we're talking about expressions with binary operators that take two operands. So it really fits nice into a binary tree structure. So this is one place where we want to use this data structure. If we want to store expressions for later use and have different applications for them. I get to the end. Oh, I thought I had too many slides there. Any questions on this? Brings us back to the last question. It's a lot of trees in one day. It's fine for you to have questions. Yeah, it's like a forest. Oh. No questions. All right, we'll have some time to walk around, answer questions about the lecture. Question? I'll leave it up. Lights on. Switch off, and I'll see everyone Wednesday.